You probably wouldn't expect to find a nuclear reactor being developed in the middle of Copenhagen, but just across the canal from here, in an ordinary-looking industrial building, there's a team working on something potentially extraordinary, a compact thorium molten salt reactor, manufactured entirely in a factory and small enough to ship on a truck. I'm Rosemary Barnes, founder of Partalo Consulting, where we advise on clean energy technologies, helping startups with development and investors with assessing the landscape. Welcome to Engineering with Rosie. Small modular reactors were meant to fix the biggest problems in nuclear power, the long construction timelines and massive price tags. The idea was to shift most of the work into factories, where components could be mass-produced, quality-controlled, and shipped out like kit parts, speeding up timelines and bringing costs down, just like we've seen in solar and battery tech. But so far, no projects have managed to actually build this way. In most cases, even when the design is labelled modular, it still ends up being mostly constructed on-site, with long delays and major cost overruns the norm. The idea was to borrow the same modularity that's helped solar and battery technologies come down in price, build components in a factory, scale up production, and avoid expensive years-long construction on-site. But so far, the reality hasn't lived up to the hype. That's why I'm so interested to see what Copenhagen Atomics is doing. They're building a molten salt reactor that runs on thorium, not uranium, and they're developing it from the ground up to be built entirely in a factory and shipped to site. It's not a downsized version of a big thermal reactor. This is a technology designed at the size it's meant to be. Now I'm about to head to Copenhagen Atomics facility across the bridge in Amager on Oliefabriksvej, which is an appropriately energy-themed street name. It means oil factory street. There, they've got nearly a full working system. Everything except the nuclear reaction in full scale. I'm going to get a tour and interview with co-founder and CEO Thomas Jem Pedersen to tell us all about how it works, the advantages compared to big nuclear, the development process, and plans for the future, including their pricing plans. Let's go. So can you tell me how does it work and how does it differ from a traditional reactor?
So first, the really important thing with molten salt reactors is that it's a liquid fuel, so you can change it while the reactor is running. And the most important part of that is you can remove fission products. So fission products is like the exhaust in a diesel engine. It's dirty and it ruins the efficiency. So you want to remove the fission products. And they're also very radioactive. So essentially there's a blanket around the reactor, and that's where the thorium is being converted into uranium fuel. But it's a different type of uranium than the uranium we use in all the other reactors. Our type of uranium is called uranium-233. So this is like a section view of the onion core, which is sort of the key invention that makes this reactor more efficient. And there's several different layers. The outermost layer here is a thorium blanket. It's roughly 1 feet thick, and it's made of molten salt. It's lithium-7 fluoride and then thorium fluoride salt at 600 degrees. So it's pumped through here super slowly, and this is where the new fuel is generated. And once the new fuel, which is called uranium-233, is generated in the blanket, it's transferred into the fuel channel, and then in the fuel channel, it generates energy by splitting into fission products. And then we have to remove the fission products from the fuel channel all the time in order to make it efficient. But I early from day one, it's much, much better than all the other classical reactors. And then the blue in here is heavy water at 80 degrees, so it's below boiling point at atmospheric pressure. And the heavy water is there to slow down the neutrons, because the probability of a neutron interacting with thorium out here becomes much higher, sort of almost 1,000 times higher probability of interaction if you slow it down with heavy water first. So that's why we need the heavy water. And actually also, if a neutron goes from here over there, you also need to slow it down, because then it will interact with the uranium-233 atom over here on the other side, and that's also a more efficient conversion when it's slow. So that the water gets hot, because slowing down these neutrons means that a lot of energy is dumped into the water. So we need to pump the water through all the time and cool the water. And if you don't cool the water, then you don't have the right geometry of the system, and then it won't work. You have to have the right temperatures in all these different layers, and you have to have the right sort of pumping speed, otherwise it'll stop working. So most of the energy, let's say 95%, goes into this heat exchanger, and it goes over to another salt that is much less radioactive, and then just to have an extra barrier we have a new heat exchanger where we go over to yet another site that we then send out in the building. And this salt is not radioactive at all. So this is a way to get from a very radioactive salt to something that is not radioactive. You can send over to another building, generate steam, and run a steam turbine.
For anything else that you would like. Okay. Yeah.
You have the tanks at the bottom. So once you stop the pumps, everything drains into these tanks and the whole fission reaction stops. So it's a very safe system. I mean, you just cut the power, you press a stop button, then everything stops. And you don't need any humans to keep it safe.
Which is the radioactive zone?
This box here, the reactor container, encloses everything that is radioactive. Then outside of that, this thick gray line is a cocoon, so you don't get radiation on the outside. But it's also there to protect from airplane crashes or whatever comes from the outside. And it's also there to protect if there was something that broke in here and you have some release, then this box is there to keep it inside. So it's the most important safety boundary is this cocoon.
Can you tell me a little bit about where you've got to in the development process and what big risks you've already eliminated, and then what's the next step?
First department here is what we call loops testing. The whole industry calls these machines loops, and they're basically there for testing components. And those components will later go into a nuclear reactor. Basically, these are just pumping salt around in a loop. So there's a part that is a furnace where we have a tank with salt, and then there's different types of setups in here. It's different depending on what it is we want to test. And then it runs for some thousands of hours, 5,000 hours or whatever. And then they usually take it out and check if everything is still okay. But this technology needs to be matured before it can be ready for commercial deployment.
The other engineering challenge that I wanted to talk about is maintenance. Similar challenge to what we face in the wind industry, that people don't understand how hard it is to design something that is not supposed to be basically ever maintained or extremely infrequently.
Part of the reason why we humans started with light water reactors is because the water is very accommodating for making it easy to build a reactor. And it is a lot easier to handle because the water doesn't become very radioactive, and also radiation in the water goes away really quickly. So you can make service and change it. But if you try to make reactors with molten salts or sodium cooled or some other medium, then everything gets super radioactive. And especially when you have molten salt reactors where you have the fuel and the fission products in the salt, and that salt goes through the pump and the heat exchanger, those things get extremely radioactive, and there's no way we can repair it. From the very beginning of Copenhagen Atomics, we gave up on that idea. We said, okay, we have to make it last for a long time. And when I say a long time, it's something like 5 years. And then we have to replace all these components that wear out. It's the pump, it's the heat exchangers, it's the reactor core. You also see in light water reactors, part of the reason why they have to replace the fuel is because the fuel assembly can only take so much radiation. So they actually also replace their fuel like every 2 or 3 years. So for us to make it last for 5 years in a super radioactive environment would be pretty good. This is how when we buy the salt from suppliers, it looks like this, just powder. And then we mix it here and we dry it. We have a special process for drying the salt. And this means that we can minimize corrosion. And then we have a number of valves we have developed, filters and other components. Then this one is the next version of the pump. It's essentially the same motor as over there, but this one has the magnetic bearings, which means that the rotating parts are levitating on a magnetic field. And this means that there's no wear when it's running. And ideally, it should be able to last for many, many years without service. Because once it's inside a nuclear reactor, it gets extremely radioactive. So there's no way you can service it. It's important that it doesn't need service for 5 or 10 years. And now that we can make it out of stainless steel, it makes sense economically to replace it every 5 years. And then, of course, that thing you replace is radioactive for a few decades and has to cool down. But then let's say 50 years later, you can remelt it and reuse it. So it's just stainless steel that you can remelt and reuse. That's also one of the big challenges, that it's a complete change of how the nuclear industry used to think, because they used to think, okay, we have to replace these fuel assemblies, and now we come along and say, and now we have to replace the oil primary circuit, but we keep the fuel. We don't replace the fuel. The fuel can be reused again and again for 100 years because we keep on cleaning the fuel. So that's what is the big difference between solid fuel reactors and molten reactors.
Can you talk a little bit about how you plan to, or how you envision these reactors being arranged in projects?
People have been used to nuclear reactors for many decades, these giant buildings, and they think this is the only way it's going to work. And we found a different way.
It turned out that the optimum size for this type of onion core that we have developed with our type of neutron economy and running on thorium, having the thorium in the blanket, is roughly 2.5 meters in diameter. We were really lucky because that's roughly the size of a shipping container. So we'd actually put these reactors in shipping containers. And then we thought of this process where we would mass manufacture reactors on an assembly line. It doesn't make economic sense at the moment to just put one unit on a site. We have to put many units next to each other. Today, solar cells are like this size, and it doesn't make any sense to make them 10 times bigger. You just put more of them at the same site. So it's the same for us. We want to put many reactor units on the same site, maybe 50 or 100 units on a site.
And a unit is 43 megawatts, is that right?
Yeah, 42, 43 megawatts.
Okay,
yeah.
So 50 to 100 would be like 2 to 4 gigawatts?
Yes.
This is what it would look like, a commercial power plant where we have a full array of these reactor units. Each one of these is a cocoon, and then inside we have the reactor container. So there would be one reactor inside each one of these, and then some tanks and other stuff that needs to be in there. And these are roughly 30 meters long. But again, this is a whole nuclear reactor with the shielding and everything. This site we have here is in the city of Copenhagen, and because Denmark doesn't currently have a regulatory authority that can approve a nuclear reactor, we don't expect to be able to run reactors here. So we're going to build the reactor here and put it on a truck and drive it to Switzerland, and then we will test the nuclear chain reaction in Switzerland. And then once we're done doing that, we can drive it back here and do some more testing here. We do expect that we can build the first 10 commercial reactors here, but eventually we will need some sort of gigafactory somewhere in the world, probably not in Denmark, but somewhere where there is a big site or big customers. The goal is to mass manufacture these reactors, at least one unit every day. We need a big site when we become allowed to install maybe 100 units, and then we can install all of those there.
Energy is really, really central to having a prosperous society. And if we can get the price of energy down, then we can create more prosperity for more people all over the world. And of course, ideally, not only should we get the price down, but we should also make it clean energy so it doesn't damage our natural environment.
So that was an amazing tour. I'm so excited that I got the opportunity to make this video while I was in Copenhagen. It is so interesting to see a nuclear reactor being developed in this totally unassuming building, like right in the heart of Copenhagen. I really love their engineering approach. They have identified the biggest problems with nuclear, and they are just systematically solving them in this very building. Very soon they're going to address the biggest one of all, building a reactor in the factory and then transporting it to site. This is the promise that other small modular reactors have promised, but just not delivered on. Too often we see people calling something a small modular reactor, but in reality, it's all built on site, bespoke every time, and not delivering on any of the promises of modularity. I think one of the key differences is this is not like a technology that should be big, a thermal reactor that needs to be huge to be efficient, that they've then, tried to squish down. This is the technology at its right size. The dimensions of the one that we saw today, that's the dimensions it's going to be. It can't be bigger, it can't be smaller, that's just it. So in my opinion, this systematic approach and de-risking in a cheap way where it's possible to, that is the way to develop technologies. You find out really quickly if the biggest risks can be solved or, if you should call it quits. I think it's got such a better chance of success than the other alternative of building an SMR on site and then hoping later to figure out how to mass manufacture in a factory. So thanks heaps to Copenhagen Atomics for this tour. Thanks as always to the Patreon team team who support this video, all videos. If you would like to see more on-site tour videos like this, then consider signing up. You can do so at this link. And thanks a lot for watching, and I'll see you in the next video.